Hello guys, and welcome back to Introduction to Number Theory. This time we will discuss the law of quadratic reciprocity. First, let me remind you of Legender's symbol, which is denoted as A over P and parentheses. Well, you understand that it has nothing to do with fractions or it has nothing to do with combinatorics. It is a symbol that denotes either 0 if A is divisible by P, or 1 if A is congruent to some x squared modulo P, or to minus 1 if there is no such x that A would be congruent to x squared modulo P. So A symbol of A modulo P is 1 or minus 1, whether A is or is not a quadratic remainder modulo P. Now let us study several theorems, several facts about this symbol. First of all, the symbol of 2 modulo P is equal to minus 1 to the power of P squared minus 1 over 8. Well, it indeed seems a bit complicated, but you'll get used to it on the one hand. And on the other hand, please do not be afraid. This power to which minus 1 is raised is indeed always integer. Let's just notice that P squared minus 1 can be decomposed into two factors, P minus 1 and P plus 1. And these two, P minus 1 and P plus 1, are neighbor even integers. So one of them is divisible by 2 and the other one is divisible by 4. So their product is divisible by 8. And here in the Legender's symbol 2 modulo P, of course, minus 1 is raised to some integer power, so it's either minus 1 or plus 1. Of course, it works only for odd prime numbers P. Well, okay, so we know the value of 2 modulo P, I mean the symbol of 2 modulo P. What about 2 prime numbers, P and Q, both odd, which are of course not equal to each other? Is there any way we can establish the connection between the symbol of P modulo Q and the symbol of Q modulo P? Well, this is indeed the law of quadratic reciprocity, and it states that the product of these symbols, P modulo Q and Q modulo P, is equal to minus 1 to the power. And this power is the product of two fractions. The first fraction, P minus 1 over 2, and the second fraction, Q minus 1 over 2. It really looks complicated, but be patient. Actually, you'll get used to it, as I already said. Let's dig a bit more deeply inside this formula and see in which case we get plus 1 and in which cases we get minus 1. It's easy to see that if one of these prime numbers, P or Q, if at least one of them is congruent to 1 modulo 4, which means that it's of form 4k plus 1, well, in this case, the minus 1 on the right-hand side is raised to even power, which means that the symbol of P modulo Q is equal to the symbol of Q modulo P. And in the second case, if both P and Q are congruent to 3 modulo 4, which means that they are both of the form 4k plus 3. Well, in this case, minus 1 is raised to an odd integer power and is equal to minus 1. So from this it follows that the symbol of p modulo q is equal to minus the symbol of q modulo p, which means they're opposite. And this is really astonishing, because from this it follows that if we take two prime numbers, both congruent to 3 modulo 4, well, for instance, I don't know, 23 and maybe 19, then exactly one of these primes will be a quadratic remainder modulo the second one. So I think that's really interesting. Well, let's consider just an ordinary example where we need to find out whether 7 is a quadratic remainder modulo 101 or not. So first of all, we write the quadratic law of reciprocity, where we take the symbol of 7 modulo 101 and the symbol of 101 modulo 7. So we know that it is equal to minus 1 to the power of something complicated. Well, you see the formula on the slide. Let's calculate this and let's conclude that the symbol of 7 modulo 101 is equal to the symbol of 101 modulo 7, which means that there are either both quadratic remainders modulo each other, or both not quadratic remainders modulo each other. So this happens simultaneously. Okay, so now calculate the symbol of 101 modulo 7, and we can, of course, switch 101 to its remainder modulo 7. So we make the substitution. We understand that 98 is divisible by 7, so we subtract 98 and 3 is all that remains, so it's called remainder. And now all we need to check is whether 3 is or is not quadratic modulo 7. For this purpose, we can build a table of all remainders modulo 7 and just make sure that 3 is not present in the lower row. So 3 is not quadratic remainder modulo 7. So this symbol is equal to minus 1, and so is the symbol of 7 modulo 101. Finally, the conclusion is that 7 is not quadratic remainder modulo 101, and there exists no such integer x such that x squared is congruent to 7 modulo 101. So this is a typical example of using the law of quadratic reciprocity.